Hello everyone, welcome to this video. And in this video, we will try to derive the famous Black-Scholes equation in the financial market. So recently, I started to interest in the financial market, and especially on the option trading. And I watched some basic training on the option trading, and there was a put basic concept of put and call, and also there's a so-called option Greeks. There's a lot of sensitivity factors, and which is very similar to the area I'm working on. So I think probably there must be a equation or differential equation to get these so-called option Greeks. That's why I get into this rabbit hole, and eventually I find this Black-Scholes equation, and which is very interesting. And that actually is not a surprise. In a few area I'm interested, each area has some kind of good equation or partial derivative equation. So this equation will set a foundation for that area or industry. I think this Black-Scholes equation also play a very important role in the option pricing, trading, and so on. So I I don't have a financial background, and but I did know some basic idea of the probability and a little bit of stochastic process and a little bit of calculus. So that gave me a little bit foundation to go through the derivation of this Black-Scholes equation, and I watched quite some good YouTube videos about the derivation of the Black-Scholes equation, and they are very good explained how this equation is derived. And I will notice one problem for me is I'm getting old. Although when they talk about each step, I feel very clear, but when they get to the step three, I will forget step one. So I think about it. So I will just put every step in a table so I can check all of them at the same time. For example, when I look at step four, I will know what will happen on step one, and so on. So I will use this method to derive this Black-Scholes equation, and there's nothing new. I just try to put all the information in one simple table, so which will help you to understand the Black-Scholes equation. So we will start from the nomenclature or terminology, whatever you call it. So we started with the S, which is underlying stock price. We also have the V, which is the value of the option, and the uppercase Greek pi, which is P, which is the value of the portfolio, and also there's a delta there. It's a change of underlying stock in this derivation process. And also we have W, which is the standard Brownian motion process. If you're interested in Brownian motion, you can watch some related YouTube. We're not going to get into detail about that. So now we'll start the derivation of the Black-Scholes model. So in this table, in the first column, I just listed the k numbers of the k equations. In the second column, of course, is the equation. In the third column, I will give a simple, brief description of what this equation is doing. Now let's start from the first equation. So starting from the first part of the equation, because when we see the equation, there must be a left side and a right side. So we start from, let's just assume we start from the left side of the equation, which is the value of the portfolio. So in this, when we derive the Black-Scholes equation, we just assume in this portfolio there's option V, and also there's stock S, and these two will be the components of this stock, of this portfolio. So one thing we which is our interesting is the change of the portfolio. If something changed, for example, the value of the option changed, the stock market price changed, and so on. So that's what we are interested. So in here we just use D P is equal to the dv minus delta ds. Basically, that means the change of the portfolio value is a change of the, we related to the change of the option value and the stock value. So this is the second equation, and then we will jump into the third equation. The third equation is related to the modeling of the stock price. So here, the change of the stock price is modeled as a geometric Brownian motion process. So the reason there's a, instead of modeling as a standard Brownian, actually we can see this standard Brownian motion process W is part of this so-called geometric Brownian motion. So the reason here is that I think the standard Brownian motion usually have a zero mean, and this geometric Brownian motion actually provide a portion part called, the first part is called the drift, the second part called the volatility. So how you understand this part, I mean, just from the option price part, stock from the stock price part, you can understand that the drift part is more like a moving average, and then the second volatility part is the change part. Yeah, so that's how we understand it. I mean, if you are interested in the geometric Brownian motion derivation, you can look at a related video where we're not going to talk about it into detail about this. So the purpose of equation 3 is because there's a ds in equation 2. We want to figure out what ds equal to. So that's the reason we have the equation 3. Then from equation 3, we just square of equation 3, we got equation 4. And which this part is very simple. It's just like a plus b square, and we just do the a square plus 2ab plus b square. So there's just more letters here. So after we did all the square operation, we have this long equation, long calculation in the middle, and which looks very complex. And then luckily, there's something called Ito's lemma, in which, to my understanding, is a stochastic calculus. I mean, that's another area I'm not very familiar with, but I just did a quick look, and from this Ito's lemma, there's a few things here. For example, the dt multiplied by dt is 0, dt multiplied by dw is 0, but the dw multiplied by dw is dt. That's pretty much is a, it's very important to simplify this big equation to this shorter equation. Basically, from here, we know that ds squared is equal to sigma squared multiplied by s squared multiplied by dt. So basically, the equation 3 and the equation 4 gave us the expression for ds and ds squared, which will be used later. So now let's go to the step 5. Because for step 3 and step 4, we already talked about the second part of this change of the portfolio value, which is related to DS. Then for the step 5, we're trying to figure out what's detail, what's neighborhood for the change of the option value. So in this one, and it's just a dv, it just do a partial derivative thing here, and we just use a Taylor expansion for the dv here. I think the key point here is you have to decide which order is relevant, which order is not relevant. So here, because the v is a function of t and s, so we did a partial v partial t by dt. If you can, this is first order, you can go to the second order, but because we can see when the dt very small, the dt square will be 0. So for the part related to t, we just keep the first order for the Taylor expansion. But related to the second part of which relate to the s, we will keep the second order for the Taylor expansion. So now we have, according to the equation 5, we know what does dv look like. So now we notice the dv, we have ds, we also have the ds square. And we already know that from the step 4, we have ds square. So we pretty much just use the 4 to replace the ds squared instead in the equation 5, and then we got equation 6. Now we have a equation for dv, which is related to time change and the price change. So we will keep this equation 6 here. And now we go to the next step. So since we already have the dv, and so we can use this equation 6 to replace the dv in the equation 2. Then we just simply put the equation 6 in here. After a few manipulation, we got this equation. So basically the change of the value of the portfolio, one first part is related to the time, the other part is related to the stock price change. And then we will have pretty much we have a good expression or formula for the portfolio value change, which is a function of the change of time, change of stock price. Then the next step will be very interesting. I think this is a pretty interesting step. So after we have the equation 7, and we can make this delta. Is this delta sound familiar to you? Actually, it is. Yeah, right. That's the option Greek delta. You can see it's a change of the option value related to the change of stock price. So we just make this delta equal to this. And if we do this, the second part of this equation 7 will become 0, and we only have first part left. So this part makes the delta equal to this is actually the so-called delta hedging. So if you're interested in delta hedging, you can look at delta hedging related YouTube. Is the concept is very simple, and why we needed to do this delta hedging here to make this do the delta hedging, because if we do this, the second portion, it's a directional change of stock price risk is gone. And basically, if we do this, we got a risk-free portfolio in the stock market. So at this step, we can see the left side of the Black-Scholes equation, we pretty much have it here. Now we need to, since we already have a left side, we need to find a right side to make an equation. So then this is another, I think, is very wonderful thinking here. So then the idea will be, I mean, since this is risk-free in the stock market, and if there's no risk, that basically means, I mean, if I put it into a risk-free portfolio in the bond market, the value change of portfolio should be the same. This is a very good idea because the whole purpose of this equation is to use the value option. So a price value and a price option. So yeah, they just create this two risk free portfolio changes, and then this makes them equal. So basically here, because we already know what is a pi equal to. So just in this equation 9, basically just a risk-free portfolio in the bond market. Let's assume, and then we put this we use equation 1 to replace the pi in equation 9. We got this, and basically this will be the right side of the Black-Scholes equation, and then we had at equation 8, we got a left side. At the equation 10, we finally have the right side of the equation. Then we just simply make the equation 8 equal to equation 10. Then we will have a equation after a simplification and move combine the similar items, so we get this equation. This will be the final form of the famous Black-Scholes equation, and some people actually call it a trillion dollar equation. And this is, you can see the structure of this equation is a pretty much a partial derivative equation. Is a so-called PDE, and we can see the derivation of it is pretty elegant, and there are a few assumptions, for example, the delta hedging and the risk-free and the constant sigma, which variance, and so on. And this pretty much is a foundation for the option trading. And those so-called option Greeks, some we can see them explicitly here, like the volatility, the dirt, and so on. And that's pretty much of the derivation of this equation. And after the equation, you have equation. The next step will be solve the equation. That will be another elegant part of this equation. In my own area, we do have my area pretty much is the foundation is one set of equation and one set of differential equation, and we don't have if you have differential equation, if you have equation, you are two way to solve. One is a numerical way, the other is you can get a so-called analytical solution. Basically, the solution is a formula. And in my area, those two set of equations, there's no analytical solution. You have to use some kind of numerical way to solve it. And the good thing about this equation is they do have an analytical solution. They will pretty much give you the price of the call option and the price of the put option. And we will talk about the how to solve the equation and how to use the solution in the future video. And this is pretty much will summarize this whole video. And thanks a lot for your time. And hope to see you in the next video. Thank you. Bye.